Hello, students! Hey, let's take some time today and talk a little bit about air pressure. Let's just jump right in. Here we go. All right, so there are some things that we already know about air pressure. Let's take a moment to review those. Number one, we know that air pressure is the force, we know that just pressure in general is the force exerted per unit of area. And essentially, you guys, that's how much force particles of matter are pushing on something. All right. Next, we know that air pressure in the atmosphere is the result of particles, otherwise known as molecules of air, being pulled toward Earth's surface. Next, we know the closer you get to Earth's surface, the higher the air pressure. And we know that just the right amount of air pressure is critical for life on Earth. Too much, and you end up getting crushed like you would on Venus. And too little means we suffocate because there's not enough air to keep us alive and our brains functioning, which is a bummer. All right. So, and again, you guys, the idea of air pressure being greater, closer to Earth's surface is illustrated in this graphic that you've seen before that shows you that the majority of Earth's air particles are closer to Earth's surface. And again, that is due to gravity. All right. So we are always keeping that in mind. And so what we know is that here down in the lowest level of the atmosphere, in the troposphere, our air pressure is the greatest, which is a good thing. And as we go up, it gets less and less and less. Okay, so let's do some boring facts for a minute. Let's talk a little bit about how we go about measuring air pressure. So it's measured with a device called a barometer. And as we get into more weather stuff, we're going to talk a little bit more about instrumentation. And so the idea that we can talk intelligently about weather instrumentation becomes important. Barometer is one of those critical pieces if you're going to talk intelligently about weather that you have to understand. All right, so normal air pressure at sea level is 1,013 millibars, which is a unit, or 29.9 inches of mercury, which is another unit, and those don't mean much to you right now. And that's fine because as we go through in the next couple weeks, they will start to mean more and more to you. So all you need to know right now is those little numbers right there. We used to use mercury barometers because as far as barometers go, they're very accurate. We don't use mercury barometers anymore because mercury is toxic. Now we use something called an aneroid barometer. They're not quite as accurate as a mercury barometer, but they are much less likely to destroy your brain. So yay, aneroid barometers are the greatest! Okay, let's watch this amazingly excellent video on how barometers work. Now, this is a fairly advanced video, and there's some concepts in here that they talk a lot about that may not make a ton of sense to you. I will break it down for you a little bit after the fact. So let's take a moment and let's watch this video on how barometers work.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist, because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Toricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Toricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Toricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Toricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Toricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Toricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
All right, cool video, lots going on. Couple things to remember, you guys, as far as what barometers look like. So this is your old-timey mercury barometer right here, and this is your new modern aneroid barometer. And again, the big difference, you guys, is that this one, essentially, you have air pushing down on mercury, and this one you have air squeezing an airtight box. So let's kind of break down what was in this video. To sum up what we saw was that mercury barometers are made with a dish of mercury, and when air pushes down on the mercury responds very quickly. The mercury rises up in a calibrated tube, and that's a fancy way of saying something we can use to measure. That calibrated tube, we measure the height of mercury, and that lets us know something about our air pressure. But again, you guys, mercury is toxic. We don't use it anymore, so today we use aneroid barometers. And because mercury is toxic, aneroid barometers are these little airtight boxes, and they can detect changes in air pressure, and the boxes are so sensitive. So this little guy right here is so sensitive that as the box gets squeezed by the air, these little dials fluctuate, and they give us an idea of where the air pressure is. Now, remember what I said before about normal air pressure being 29.9 inches of mercury? That's the reading if we're using a mercury barometer. And I said that normal air pressure is 1,013 millibars. As you can see, that's the reading we use if we're using an aneroid barometer. Okay, you'll also use the term kilopascals depending on where you're at. Just for everybody, person on the street sort of thing, you're going to hear inches of mercury, or you're going to hear millibars. Okay, so, and again, you can see that's what this little thing is telling you right here. This is telling you this is about what normal pressure is. So right now, if we're looking at this aneroid barometer, we can say that, hey man, the air pressure is actually pretty high right now. Okay, so that brings us again to this idea, is that here's a fun fact for you, is that air pressure can change. Okay, wait, you might say to yourself, what do you mean air pressure can change? Air pressure can change, and it can fluctuate depending on certain conditions, and let's take a look at those certain conditions. The certain conditions, you guys, have everything to do with whether air is rising or falling, and allow me to explain in this incredibly entertaining video. This is Joe, Joe represents air. When air falls, the pressure on the ball increases. When air rises, the pressure on the ball decreases. That's how it works in nature. Rising air equals a decrease in air pressure. Falling air equals an increase in air pressure. It's an inverse relationship. Cool. Yeah, that was a really entertaining video. I think it was very good. All right, so what causes air to rise and fall? It's very simple, you guys. It's temperature and density. It's temperature and density. It's temperature and density. It's always temperature and density. Because what we need to remember, you guys, is that cold air is more dense, and so it falls towards Earth. Warm air is less dense, and so it rises away from Earth, okay? And if cold air is falling towards Earth, it means that air pressure is going to increase because, like we said in the video, it's an inverse relationship. Falling air means an increase in pressure. Rising air means a decrease in pressure. So I need you to remember something, you guys. This goes back to this idea right here, this idea of convection, okay? And again, if we're looking at this, you guys, we have heated material that rises, it gets away from its heat source, it cools, and it falls back down. And as these things, as this air rises and falls, that causes a change in pressure. Again, falling material, we have an increase in pressure. Rising material, we have a decrease in pressure. And if you get stuck with that, you guys just think of Joe sitting there, he's representing air, that if he sits on that exercise ball, the pressure on the ball increases, and when he stands up, the pressure on it decreases. Okay? That's always a visual that you can go back to. Here's another one that we're going to go back to. Just remember that temperature and density change when we change heat sources, and that goes back to this picture that we looked at last week, you guys, in the concepts of radiation, where the sun heats the surface of the earth, conduction, where the surface of the earth gets hot and it heats up the other parts of the surface of the earth and all of the air around it, and convection, where that warm air rises and all kinds of cool stuff happens. We change air pressure when that happens. We start to make clouds when that happens. So all this stuff that we've been talking to, we're starting to put the pieces together in terms of what we're doing in the atmosphere. How we heat the atmosphere, what happens to the air affects air pressure. And as you'll see, the reason that we care about this is because ultimately, you guys, we're getting to this right here. We're looking at a tornado, and that all of these things are related. So if you're going to make a tornado, all of the things that we're talking about are pieces of the puzzle that go into making this thing right here. So as we move into the next couple weeks and we really start talking about the phenomenon of weather, we have to have this really awesome understanding about how air is behaving in our atmosphere. And that's what we're doing right now, you guys. We are building the pieces so that we can put together this puzzle of why something like this happens in our atmosphere. All right, you guys, good work today. Well done. If you have any questions, let me know. Toss me an email, give me a phone call, join me for office hours right on.